What is the acceleration of a solid metal sphere that rolls down an incline that makes an angle theta with the horizontal? So we may have some familiarity with things moving down an incline in this class since we've looked at that before. But we've done experiments, right, with like a cart going down a relatively frictionless air track, or we've imagined objects going down a relatively frictionless incline. But now we're talking about an object rolling down an incline that is a solid metal sphere. And the only information that we're given here is the angle. And maybe just for fun, even though this question is expecting an expression, but I think it might be cool to actually get a number. So let's say we had a 5-degree incline like that, and I want to calculate what the actual acceleration is going to be. And one thing that might strike one as weird is like, well, does it matter how big the sphere is? How come I'm not being told what the radius is or what the mass is? Well, let's find out. I mean, hopefully we won't need those things, right? Since it doesn't give it to us, right? Or it doesn't give us those. But since we weren't given any number, maybe we were just supposed to like label those with an M or an R or something like that. So I'd like to do a force-based analysis on this first before I even start doing any like equations. I was going to say physics, but I think in some ways drawing pictures of forces really is doing physics, and writing equations not so much. I mean, it's part of it, right? But it's really the pictures what captures the idea. So pretty clear. All right, we've been learning for a while now that anytime you start a force diagram for something doing something on Earth, right, there's always going to be a weight force. So F sub g. I think there'd be a normal force here. Hang on. Let me try to make that sort of match my picture. This is the hardest part for me. So if your pictures aren't perfect, join the club. All right. Do I need any other forces, right? Like when we did an object sliding without friction down an incline, we wouldn't include friction. If we had an object just sitting in place on an incline, we would put static friction. What about rolling? Do we need to have friction there? And I think the answer is yes, we actually do, because if there were no friction and you just let this object go, there would be nothing to make it start kind of turning around, nothing to make it rotate. It's friction with the surface that it's rolling upon that actually makes the sphere rotate. And if it does that without slipping on this surface, that's actually going to be static friction. And one of the things about static friction you might recall is there was that inequality that kind of described its relation to its coefficient of friction. I was not given a coefficient of friction here. So all I really need to assume, I think, is that the amount of friction is sufficient to make it so that this thing rolls without slipping, right? That means as a quantity, this force of friction is going to be unknown, but it's a necessary part of the story. And we're trying to find acceleration, of course, right? So there's acceleration kind of down the incline there. It might make sense. I mean, if we weren't doing a rotation chapter, wouldn't we just do F equals ma for something like this, right? Of course, we're doing a rotation chapter, and in this topic we introduced tau equals I alpha. Maybe we should start with that. I'll tell you what, we're going to do both. So we'll do F equals ma, Newton's second law, and we'll do tau equals I alpha, Newton's second law for rotation. And we're going to use these pictures to kind of make sense of all of that. Okay. So for F equals ma, I think it makes sense to me that we would use maybe a rotated coordinate system here. So I'm just going to draw up here somewhere in space like a rotated xy coordinate just to establish that that's what I'm doing. There it is. And I think if I look at the x components for this really should have been a vector equation, right? So maybe it's not proper for me to have not put vector notation there. I'll put that in now because we could do x or y components. Maybe x components is going to be sufficient. And if I look at this, like what's going to happen there, right? I've got force of friction, force of gravity, normal force. Normal force is not in the x direction, so I won't need that. I'm going to go ahead and be explicit already in this step, but not put everything in. I think that force of friction, that one kind of strikes me there in the free body diagram. I'll start with that one. So there's going to be that, but there is, and it's going to be minus, right? Because x points kind of rightward and this one's pointing leftward. But there's also a component of gravity, right? If you can imagine, like looking at that gravitational force. Right, so I'm just going to draw a larger picture of it here so I can kind of share what I'm thinking in my head here. If I were to break that into x and y components and kind of get a component triangle, it might look like this. In other words, that's kind of the f sub g sub y part right there, and that's kind of the f sub g sub x part. So it clearly does have a positive component in the x direction, right? So maybe I could write here there's going to be a plus f sub g sub x is equal to mass times acceleration. Okay, what can I do with that? I don't really know anything for this friction because I said it was an unknown, so we're just going to leave that alone. But the f sub g sub x, I think I can do something with that because we know that f sub g itself is equal to the weight mg. I think in this triangle I drew, the angle, which, you know, maybe if I'm doing this without, I said I'd eventually do this for 5 degrees, but let's say that that is symbolized by theta because the actual question we were asked here didn't give us the 5 degrees. I just said it might be fun to actually test things out and see if that works. So for now, I'll just use theta. And I think that this x component should be then equal to mg sine theta, since it is opposite to the angle that I think is fairly clearly equal to the angle of the incline. So that means I can put over here plus mg sine theta equals ma. Now, if you recall how things went for an incline or an object sliding down an incline without friction, we didn't have this part. So at this point, we could cancel masses, and we would just get a equals g sine theta. And that's something we've seen before. We've kind of tested that a bit in the lab, I think. So cool, right? But not cool because I've now got this and I can't cancel masses. What do I do, right? Well, the thing is, that's the force that rotates this sphere. So that's the one that is applying a torque around the rotation axis of the sphere that represents the fact that it's rolling. So that's the one I'm going to maybe use in this tau equals I alpha situation. In other words, I'm going to say that if r represents the radius of this sphere, so I'm just going to throw an r in here, even though I wasn't given an r, but it has to have a radius, right? And it had to have a mass too, so I'm perfectly fine with throwing that in. I'm going to hope that this radius cancels out in some way at the end of the day, just like the mass hopefully will cancel out like it would have done if this were not a rolling object. For a sphere, the moment of inertia is 2/5 m r squared, and then we've got alpha. So that's what I get from looking at the rotational part here. I can cancel out one of these r's, and then what I can do is recognize that r times alpha is equal to the linear acceleration a. So this is pretty cool because now I could take this expression I got from analyzing the rotational physics for this force of friction and maybe substitute that in here, and I would get minus 2/5 ma plus mg sine theta equals ma. And wow, all the miracles I was hoping for have happened here because there are no more r's left and all the masses have canceled out as well. And so maybe if I just add 2/5 a to the other side, I would get like g sine theta is equal to 1 times a plus 2/5 times a. I think I'm just going to combine that right now and say 7/5 times a, suggesting that a is equal to 5/7 g sine theta, which for theta equals 5 degrees, I could put into my calculator, I just put 5/7 times 9.81 times sine of 5 degrees if I have the calculator in degree mode, and that gives me a result of 0.6107, and that should have units of meters per second squared that it gets from the g value that I use. So you can check that if that's what you get for 5 degrees. But what's amazing really is I really only needed to know that angle in order to calculate. The thing we'll be able to check on the slide though is just this expression. So let's go ahead and do that. And there it is.